Hello my people. We're going to be talking about in this video and the ones to follow parametric equations and the derivative. So basically differential calculus applied to parametric equations. So let's go ahead and start off with this example that I've given us. Now let us suppose we have the following set of parametric equations, and x is equal to t minus 1 over t and y is equal to 1 plus t squared. Now suppose we are asked to find the equation of the tangent line when t is equal to 1. Okay, well, so we know we need two things for the equation of any line, right? We need a point and we need slope. Hence, point slope version of a form of a linear equation. So if I want to plug in 1 into here, I'm going to get 1 minus 1 over 1, which is 0. And I'm plugging 1 into here, and I'm going to get 1 plus 1 squared, or 2. So my ordered pair is 0, 2. Okay. Next, we need to find the derivative. And the formula for finding the derivative is simply taking dy over dx. And since I'm looking for dy dx, but I'm looking for it in a pair of equations that are stated in terms of t, what I need to find is I need to find dy dt, and I need to find dx dt, and of course the ratio of those would reduce down to dy dx. So let's go ahead and find those. Now remember, your x is t minus t to the negative 1, and your y is 1 plus t squared. Okay. So what we get here is we get 1 plus t to the negative 2, and we get that over 2t. Actually, that's backwards. I get 2t over 1 plus, basically 1 over t squared. Now, if I want to evaluate that, I could go ahead and clean that up if I was actually using it for another purpose than just evaluation. So what I need here is 2 times 1 plus 1 plus 1 over 1 squared. So it's 2 over 2, or just 1. So I have my point, I have my slope, I have my point, and so what I really need is simply y minus y1 is equal to m times x minus x1, or y is equal to x plus 2. Now, what we get here is, if we want to go ahead and see if that is a tangent line at the particular point, what we get is x plus 2. So we're going to go through that point right here. And since it's a slope of 1, we can go ahead and mark at negative 2 along the y. And that right there is y is equal to x plus 2. And it does indeed appear to be, at least eyeballing it, the tangent line at 0, 2, which of course is the point where t is equal to 1. Alrighty. Now that we have that first example out of the way, let's go ahead and move on to a couple more. Okay. So we have x is equal to 4 sine t, and y is equal to 3 cosine t. Now you should recognize this already as an ellipse. It is one. And we need to find the equation of the tangent line at t is equal to pi over 3. So let's go ahead. Remember that we need a point and we need slope. So let's find the slope first, since I know you're eager to take the derivative. And I know that we need dy dx is equal to dy dt over dx dt. Now dy dt is going to be negative 3 sine t, and dx dt is going to be 4 cosine t. So what we have here is we have negative 3/4 tangent t, but since I'm going to be evaluating it, it might actually be a good idea just to leave it like that, since usually, for the most part, people figure out the unit circle values for tangent by doing the sine and the cosine together in their head. Well, if you already have the sine and the cosine right there, why change it if you're just going to have to change it back in your head, right? So -3 times sine of pi over 3 and 4 times cosine of pi over 3. Now, sine of pi over 3 is going to be √3 over 2. So we have -3 times √3 over 2. And we'll just go ahead, and this is going to be 1/2. So this winds up being -3/4 √3, or, you know, if you want to put it all in terms of a single expression, it's that. So basically, at t is equal to pi over 3, this is the slope of the tangent line. Okay, so now we need the points. So we have x at pi over 3, and we have y at pi over 3. Well, thankfully, we've already evaluated sine and cosine. We just have to kind of swap it, right? So it's 4 sine of pi over 3. So it's 4 times √3 over 2, or 2 √3. This is going to be 3 cosine of pi over 3. That's going to be 3 times 1/2, or just 3/2. Which means that I have my ordered pair. My ordered pair is 2 √3, 3/2. So I have y minus y1 is equal to my m, and then x minus x1. And you're like, yeah, it's a lot of radicals and fractions and stuff like that. Surely that is not the case. Well, that is actually what transpires when we actually plug in both of those into Grapher. Of course, the ellipse is here, and this right here is my tangent line of y minus 3/2 is equal to -3 √3 over 4, x minus 2 √3. Okay. Alrighty. Well, let's go ahead and move on to our next example. We're going to find the equation of the tangent line to the curve at the corresponding point, given, basically that corresponds to the given value of the parameter. Okay? Now, the parameter is theta is equal to pi over 6. Now, if you don't remember what this looks like, this is that asteroid. Basically, it's that star. Okay, and when we actually see it, it'll look something. If you actually, graph the whole thing, it's the one that looks like this. Okay, and we've dealt with that in a couple of different problems. Now, what we need to do from here is, of course, if we're looking for the tangent line, we need, of course, point and slope. Let's again do the slope first. Now, you think that it might be nasty, but it actually is not going to be. My dy dt is going to be 3 cosine squared theta over negative sine theta. Dx dt is going to be 3 sine squared theta over times cosine theta. And of course, when you put these over each other, you're going to get a lot of cancellation. And so we get 3 cosine squared theta, it's going to be negative, times sine theta, over 3 sine squared theta cosine theta. This sine cancels with one of those. This cosine cancels with one of those. Those 3's cancel out. And what I'm left with is simply negative cosine theta over sine theta, or if you want, negative cotangent theta. Now, if we're going to go ahead and evaluate this at theta is equal to pi over 6, we get negative cosine pi over 6 over sine of pi over 6. Now this, of course, is the reverse ordered pair from the last problem when we were dealing with sine and cosine evaluated at pi over 3. We know that cosine of pi over 6 is negative √3 over 2. Sine is positive 1/2, and I'm left with negative √3. That right there is the slope of the tangent line. Now we just need to find the points. And so what we have here is we have x of pi over 6 is going to be sine of pi over 6 cubed, and then y of pi over 6 is going to be cosine of pi over 6 cubed. Well, sine of pi over 6 is, of course, 1/2, and when you cube that, it becomes 1/8. This is, of course, root 3 over 2, and when you cube that, it becomes 3 root 3 over 8, or if you want to leave it, it's root 27 over 8, whichever. Now, we have our point, we have our slope, we have y minus 3 root 3 over 8 is equal to negative root 3 x minus 1/8. And if we zoom into the asteroid where it actually happens, we recognize that at this point right here, that is the tangent line, okay? And it actually does. It looks like a legitimate tangent line at that particular point. So, and remember, just in case you don't remember it from its parametric form, this is what it looks like in rectangular, and we have dealt with that before on several different occasions. It's kind of a fun one. Alrighty, moving on. Okay, now this one asks us a tangent line problem, but it asks us a little different. And so what we want is we want to go ahead and find dy dx so we can answer any question that we actually have to. So dy dt is going to be 2t, and dx dt is going to be 3t squared minus 9. Now what that means is dy dx is 2t over 3t squared minus 9. And if you pull the 2/3 out, you get t over t squared minus 3. Now that may not look like much because you can't officially factor that, but you can sort of force factor it and just treat that as if it were a difference of two squares, revealing the fact that you have two values that will make the denominator equal to 0. So excuse me. My horizontal tangent line is going to be where t is equal to 0, because the derivative is 0 where the numerator here is 0, and t is equal to 0 when t is equal to 0. And then of course we have vertical tangent line is going to be at t is equal to plus or minus root 3. Now, if you actually wanted to find the ordered pairs, which it actually does ask you for, you simply need to evaluate both x and y in terms of these t values. So we have x of 0, y of 0, x of negative root 3, y of negative root 3, x of root 3, and then y of root 3. Now, let's go ahead and plug in. You're going to get 0 cubed minus 9 times 0, which is of course 0, and then 0 squared, which is 0. This is going to give you the ordered pair 0, 0. Okay, let's go ahead and look at this one. We know that at negative root 3, we can actually, if you think it's easier, you can rewrite x as t and then t squared minus 9. And that allows you to basically put the negative root 3 out here and then 3 minus 9. And just like you can put the root 3 and then 3 minus 9 out here, just makes the arithmetic a little bit easier. And so we get negative root 3 and negative 6, which is 6 root 3, which, just in case you were wondering, is 10.392. And at negative root 3, it winds up just being negative root 3 squared, which is 3. So our ordered pair is 6 root 3, 3. And this down here is going to be the same thing. It's just going to be the x coordinate is going to be the negative. And so we have negative 6 root 3, 3. And those are the 3 points. And you're thinking to yourself, surely not. All right, well, let's go ahead and take a look at the graph. Okay. And what I have is I have this point, and I have this point. They look awfully symmetrical. Of course, we see the fact that 0, 0 is going to have a horizontal tangent line. But if I want to draw the vertical tangent line here, notice that it is just to the left of negative 10, and this one is just to the right of positive 10, which makes sense out of those approximations of 6 root 3. Ta-da! Alrighty. We'll go ahead and do one more, and then we'll call this video to a halt, and we will start up another one. This last one for this video is show that the curve x is equal to cosine t and y is equal to sine t cosine t has 2 tangents at 0, 0, and find their equations. All right. Well, again, let's find dy dt. And you don't actually have to do them separately. I'm just doing them separately for emphasis. You can go ahead and just plop them into the same ratio. Now, this right here has to be done by the product rule unless you recognize the fact that you can change that using the double angle identity. As long as you multiply it by 1/2 and by 2, it becomes 1/2 sine 2t. I'm going to use it in this form right here, and I'm going to get cosine of 2t. Now, if you did it by the product rule, you would wind up with cosine squared minus sine squared, which of course is cosine 2t as well. When you take the derivative of x equal to cosine t, you get negative sine t. So, take those two together. Your dy dx is cosine of 2t over negative sine of t. Now, you need to find out the t value that you're going to be able to evaluate these at. And the way that you do that is you actually need to take x is equal to cosine t, y is equal to sine t cosine t, and set them both equal to 0. Well, what do they have in common? They have in common cosine t. So really what you're looking for is where is cosine t equal to 0? Well, you know that that is equal to 0 when t is equal to pi over 2 or 3 pi over 2. And so you want to evaluate your dy dx at those two values of t. So dy dx at t is equal to pi over 2 and dy dx at t is equal to 3 pi over 2. I need to get, that's cosine of pi over negative sine of pi over 2 and cosine of 3 pi over negative sine pi over 2, or negative sine 3 pi over 2. Now, cosine of pi and cosine of 3 pi, those are coterminal, so they're the same. It's negative 1. Sine of pi, however, is 1, but then it's negativized. Sine of 3 pi over 2 is negative 1, and then it's unnegativized. This is 1. This is negative 1. They both go through the origin, so this is y is equal to x, and this is y is equal to negative x. Alrighty. We will venture on with some more problems in the next video. If you have any questions, please do shoot me an email. Bye.